Okay, everyone. I'm going to try to show you what I can show you and tell you what I can tell you. So we were talking about energy today. That is the new unit. We just got done with forces. And so I had asked folks, hey, do you know what the 6 forms of energy are? And so we spent some time just thinking about what those were. Electrical, as you can see, there's the top on the list. And then there was thermal. And again, I'd probably be writing these down. So electrical, thermal, and then we had radiant, which is any kind of radiation. We're talking electromagnetic waves, right? Then you have nuclear, and then we have mechanical, and that's the one we'll spend the most time talking about. And then below that we have chemical. So those are the 6 forms of energy. So again, electrical, thermal, radiant, nuclear, mechanical, and chemical. Those are usually divided into 2 categories. Oh boy. Where'd my marker go? Oh gosh, I erased this thing because it was in the way of something, and then now I need it back. So, because when asked what the 6 forms of energy are, most people refer to the term kinetic and possibly potential. Here's the thing about that. I'm going to say stored instead of potential. Sorry, I was trying to put my cap on my marker. You might have motion sickness by the time you're done with this video, who knows. So kinetic and stored. These 6 forms of energy here, most of what's happening with those can be kind of separated into the 2 ideas of kinetic and stored. Kinetic meaning motion. So some of these forms of energy are dealing with motion. Some of them are dealing with the fact that energy is stored somehow in that mechanism that we have named here. So, and some of them have both going on. So if we look at just the list here, electrical, typically, I mean, it can be both. It can be both stored, energy can be stored electrically, and it's also kinetic, because anytime you have charges, electricity moving through a conductor, that would be kinetic, that's motion. But then charges, electrical charges, can also create some stored energy. So energy can be stored in the electric fields of charges that aren't moving at all. So there's both going on there, really. Thermal, if you remember back to when we talked about thermal, we spent a lot of time talking about thermal, and thermal has to do with the motion of the particles. Remember, that's kinetic, motion of the particles for thermal. That's why they have thermal energy. That's what we defined it as, how much those particles are moving, and which makes them hot. So radiant, we're talking about waves, electromagnetic waves. And so those are moving, the waves are moving, and they have to land on something, they have to be absorbed by something to really do much. So I suppose they're energy is kind of stored in wave form that can move, but then nothing really happens to the radiant energy until it is absorbed by something. Some kind of matter has to absorb it. Then we have nuclear, so that's energy stored in the nucleus of an atom. And so that would be stored. I even called it stored by when I described nuclear. So that'd be stored energy. Then we have mechanical. And mechanical, typically, we think of both, there's different kinds. Mechanical can be separated into several different categories. And usually we think of those in terms of kinetic, or energy of motion, and energy that's stored in certain mechanical mechanisms, which we'll talk about. That's what we'll spend most of our time talking about. And then we have chemical down here at the bottom. So chemical energy, that's where energy is stored in the chemical bonds that hold the atoms and molecules together. So again, it's stored energy. It's not really useful until those chemical bonds are broken and new ones form, and then we see energy released from that process. So, what exactly is energy? Well, I would say having the ability to cause a change in one's surroundings. So, what is energy? Having the ability to cause a change in one's surroundings. That's what I would call it. Pretty basic. Very general. Very general. Like, what does it mean to have the ability to cause a change in one's surroundings? I mean, that could mean anything. And so, again, these 6 forms of energy, anything that has what we would call those 6 forms of energy, those things have the ability to cause a change in the surroundings. As vague and as general as that could possibly be. So now let's head over here. I have a little setup here. This is what we spent some time looking at. I have this thing, we'll call it an energy detector. Oh boy, we'll see if this thing stays put. I don't know how well this is going to work. So I have an energy detector here, and that's this right here. A very, very high-tech piece of equipment here. And I'm sitting it against a stack of books. And so here's what we did. We had a softball, and I rolled a softball at the detector. And what do you think happened when I rolled the softball at the detector? One. I had one energy fall out. One little, I call these things energies. I had one little energy fall out from the softball hitting the detector. See, the detector can detect energy by how the detector responds to whatever I throw at it. No pun intended. And so I asked the class, hey, is there something I can do to that ball that will allow it to possess even more energy? And they said, well, roll it faster. I said, great idea. So I rolled it faster. Oh boy, that wasn't fast enough. That was barely as fast as last time. And so I rolled it faster like that. Ooh, hey. So I rolled it faster, and we see now, instead of just one little energy, I've got 2, 4, 6, and actually there's one just out the back side here. So about 7 or so energies by rolling it faster. So apparently, how fast something is moving is an indicator of how much energy it has. So faster objects have more energy. Okay, well that makes sense. And then I said, is there something else that could be done with this ball? Another property that could be changed about the ball that would change how much energy it has. And then they said that I could increase its mass. And so I said, hey, well, it just so happens. Now, I wish it was the same size, and it isn't. But this bowling ball here, you see, it has a lot bigger mass than... Oh, boy. Oh, stop rolling. Stop rolling. Whew. So, oh, no. Oh, my goodness. I should sit on the thumb hole. I think I might stop there. So that bowling ball has a whole heck of a lot more mass than the softball. So even if the bowling ball rolls slowly, really slowly, I'm assuming that's probably going to have more energy. Oh boy, way more energy than the softball that was that slow. The softball wasn't even that slow, and it didn't have. I mean, wow, this thing has more energy. There's more energy that this bowling ball has going that slow than even the fast softball had. Now, some of it, of course, has to do with how large the ball is, size-wise. That kind of messes up the whole idea. But the point is this. More mass means more energy. Faster means more energy. So apparently both mass and velocity can affect how much energy an object has. So, let's move on. What if I set the detector? Well, hold on. Let me do this one. Because this one is, I don't know where to go. Here it is. I have a little elastic band here that I can attach around the the detector. And if I pull on this paper clip here, that stretches the band. So the question is, do you think there's energy stored in the bands from... Let me move this a little bit here. Do you think there's energy stored in the bands when I stretch them? Well, let's see what the detector says about that. Well, apparently, so you can store energy in things that are what we would call elastic, things that can stretch or compress, that can deform, and then return back to their original size, shape, and configuration. So how could I make more energy? Oh my gosh. How could I make there be more energy in the band? Well, people in class said, we got to stretch it further. So if I stretch it further, do you think that that would show that there's more energy? I hope so. Well, hopefully I can do that without breaking anything. And, oh yeah, of course. And the energies go everywhere and the crowd goes wild. So we see then that with elastic energy, sorry about all the, I'm a little phlegmy. With elastic energy, the more you deform the object, whatever it is. Now, it doesn't have to be a rubber band. It could be a meter stick. See, meter sticks have the ability to flex and bend, and then they return back to their original shape. I showed that in class by doing another little thing. Here's what I did. I took a meter stick, and I held the meter stick tight up against a desk, and I pulled the meter stick back like so, and then I let it go like that. So by doing that, I am storing some energy because this meter stick actually is flexible, and it can be flexed out of its normal shape, and it returns to its normal regular shape. So the fact that that happens, that means the meter stick is elastic, and that there are ways that we can store energy in it and then allow it to return back to its normal size and shape. So things like springs, things like rods and beams that can be bent and then returned back. I mean, even like a rubber ball that can compress and then return back, or even a steel ball. Steel has the ability to deform and then return back to its normal shape, like springs. So anyway, that is what we would call elastic energy. And then the last one we did is I put the detector on its side. Which was kind of a challenge without having to keep stuff from falling out. So I put the detector on its side. Oh, jeez, come on now, come on, cooperate. Okay, you're done. You obviously can't fit. So then I took like a ping pong ball. Where did my ping pong ball go? I took a ping pong ball and I dropped it. I dropped it on the detector like so. And when I dropped it on the detector, oh, look at that. One or two little energies came out. Oh, and then a couple more out when I pulled on those. So clearly, the ball falling on the detector, there's energy there, okay? The ball has energy. And so then I said, hey, what could I do with that ball that would make it have more energy? And they said, well, drop it from higher height. So I did. And what do you think happened? More energies came out. Oh my gosh, forget it. Then they said, hey, or I said, what can I do besides just that? And they said, well, use a more massive ball. So then I took the stainless steel ball bearing and I dropped it from just a low height, and we saw, oh, tons of them came out. All kinds of them came out. So that tells us not only in terms of that kind of energy, not only how high the ball fell from, but how massive it is affects how much energy it has. And so that's what led us to this. So let me see if I can get around here. This right here. We separated things into three categories. So again, we're looking at mechanical. And mechanical, when we separate it out into three categories, we have what would be called kinetic, or EK we call it. That's what the symbol is right there. So EK is what we would call kinetic energy that is mechanical. And it depends on an object's mass and its velocity, like the softball versus the bowling ball. Faster means more. So again, greater velocity means more kinetic, energy kinetic, and more massive means more kinetic energy. Then, well, the bottom one here is what I showed you next, and that is stored elastic energy. And it's stored with how things can be stretched or compressed. Stretching and compressing is how you store that energy. And we call it EEL. EEL for elastic. So elastic energy. And the last one I showed was gravitational. So E little g there, EG, is stored gravitational. Now, what kinds of things affect gravitational? Well, the mass of the object we saw and how high it is dropped from, or how high it is. So those three are the category. Oh boy, this camera work is pretty bad. Those three right there are the three categories of mechanical energy that we're going to spend time looking at. All right, those three categories right there. Kinetic, so whenever something is moving, we would say that it has mechanical kinetic energy. Whenever something has a certain elevation above the ground, we would say that it has stored gravitational, or EG. And if something has been stretched or compressed or twisted in some way, we would say that it has stored elastic, which we would say EEL. So that's what we went through today in class. And then we talked about this thing called law of conservation of energy. The law of conservation of energy, saying that, hey, you can't create or destroy energy. Okay? Can't create or destroy it. Which leads me to this last little diagram here. Here's what I did. I drew a little diagram of a ramp, and I put a ball here at position A, and then later on it's at position B, and then later on it's position C as it rolls down the ramp. And I put these little pies. These are little energy pie charts, is what this is. And so what we said was, what I asked the class was, at position A, before I let the ball roll, what kind of energy is there? And again, you have to ask yourself, okay, is the ball moving at that point? If you say no, then there's no EK. There's no kinetic. If it's not moving already. Has anything been twisted, stretched, compressed? If the answer is no, then you cannot have any EEL. You can't have elastic energy if nothing's been stretched, compressed, or twisted in some way. Then, does it have elevation? Does it have some height? Because remember, that's what we said about gravitational, right? Gravitational has height. Kinetic has velocity. They both have mass. And then elastic just has things being stretched or compressed or twisted or something. So we said then that the whole pie, all of the pie, is gravitational for section, or for part A, position A. Then we said, hey, for B, it's about halfway down the ramp. So half of its height is gone, but it's also moving now. So we all decided that that meant that half of its gravitational is gone, and that has become kinetic, energy of motion. So it's gained some motion, but it's lost some height, if that makes sense. So again, if we're looking at our little descriptions here, we have lost some height, lost some gravitational, but we're gaining velocity. So what we've lost in height, we've gained in velocity. So maybe 50-50. And notice the pies are all the same size. The pies are not changing size because why? Because energy cannot be created or destroyed. That's why the pies have to stay the same size. We're not growing or shrinking how much energy there is. And then finally at position C, now the ball is at the bottom of the ramp, and then the question has to be, is there any more height? No, if you have no height, it is at its lowest possible point, then we would say, okay, there's no gravitational. Is it moving? Yes, in fact, it's moving at its fastest. All of the height that the ball had has now made it become energy of motion. It's gained velocity as it lost its height. So I would say then all of the pie would have to be kinetic energy, because again, nothing got stretched or compressed in this whole process. All that we had was some height at the beginning. We had some height at the start here, and that height got less and less and less as time went on. meaning the gravitational part of the pie got smaller and smaller and smaller, until, oh boy, until eventually all of the gravitational had become kinetic. So I hope that makes sense. I know obviously we spent more than 20 minutes talking about this in class, so I tried to be as thorough as I could without being too boring. There is a worksheet that goes with this, so there should be something on Classroom for you to take a look at, and I only want you to do the first 2 questions so that we can kind of examine what's going on and figure out if we're doing things right before we get too far in. So I just want you to kind of get your feet wet and trying to, this is the goal. The goal is going to be able to interpret a scenario like an A, B, and C and figure out what kind of energy is there and be able to clearly label it and identify it. So that's all I've got for today. Hopefully you're doing well, and we will see you next time.